Hello chemists, this is Ms. Placino and you are watching Screencast 6.1 on significant figures and dimensional analysis. Today is really a fundamental lesson that we're going to really use throughout the remainder of the semester as well as the school year. Being able to do dimensional analysis, which is basically just a form of unit conversions, and calculating things to the correct number of significant figures is going to be really important as we get into more quantitative work in chemistry. So today we're going to figure out or discuss what significant figures are and how they're used in calculations. You already know a little bit about significant figures as far as certain and uncertain digits go. We talked about this very, very early on in the school year, but you might not have remembered, so we're going to address it again. Let's take a look at the do now. You place a beaker containing water on a scale in the lab and record the mass as 157.8 grams. Which digits are certain, uncertain, explain. So you can either look back in your notes or you can kind of just think about this one if you remember it, which digits are certain, which are uncertain, and be able to provide an explanation. Regardless of what tool or instrument you're using to take a measurement, there's always some degree of uncertainty. It doesn't matter if it's a fancy digital piece of equipment or if it's something like a graduated cylinder where you have to take the measurement manually. The uncertain digit is always the last digit. It's uncertain because it's been estimated. If we get the measurement 157.8, the certain digits are, in this case, the first three. In this case, scale knows that the mass of the beaker and the water is somewhere between 157 and 158 grams. It doesn't really know exactly what the tens place is. Maybe it's around here. So it's been estimated. So we say that that digit is uncertain. It's really important when you're taking measurements to estimate this last place so that you are clearly communicating which of these places you had to estimate. The smaller the value that you estimate, so for example, the tens versus the hundredths versus the thousandths, the more precise that measurement is going to be. Let's get into today's lesson. Right. Significant figures is something that tends to give new chemists a whole lot of difficulty, but it's really not so bad. It turns out there's just a handful of rules that we have to be familiar with. Anytime you take a measurement and you end up with a non-zero number, that is considered a significant digit. So the numbers 1 through 9 are going to be significant. If you end up with a zero that's between two non-zero digits, those zeros are significant as well. So in the measurement 2008, we have a total of 4 sig figs. Both these zeros are significant. In 601, we have 3 sig figs again. That zero is significant. In 50,409, these zeros are significant. So there are a total of 5 significant figures. When we have numbers that are less than 1, the zeros that are to the left of non-zero digits are not significant. This happens a lot, like I said, and we're talking about numbers that are less than 1. These lead zeros up at the front are not significant. So in the case of this first one, there's only 2 sig figs. 2 sig figs again in the second one. All 3 of these are significant because here we've got a zero that's sandwiched in between 2 non-zero digits. Fourth rule is zeros to the right of non-zero digits and numbers that include decimal points are significant. So we look for a decimal point. We've got it. We've got a zero that's to the right of a non-zero digit. 6 and 7 are both non-zero digits. Therefore, all of those digits, including the zero, are significant. For the same reason, these 3 zeros, 9.000, we've got a decimal point present, and we have zeros that are to the right of a non-zero digit. So just like the previous example, those zeros are significant as well. I know initially these rules may seem really arbitrary and kind of difficult to commit to memory, and I'm not going to ask you so much, which of these digits are significant once you kind of get the hang of this. We're going to have to be able to apply it. However, in the meantime, we probably want to do some more practice. So let's take a look at your practice problems. Let's take a look at these practice problems. I'm going to walk through questions 1A through C with you. So for question 1A, I'm trying to figure out how many significant figures are in the measurement 1,234 grams. I don't see the number 0, and that's really the only digit that causes any trouble. So I'd say there are 4 significant figures in this measurement. If I look at letter B, I've got 0.023 milliliters. Zeros that are to the left of non-zero digits are not significant. So these 2 zeros are insignificant, leaving us with just 2 significant figures. The measurement 890 nanometers. Be careful on these. This 0 is technically not significant. It is not sandwiched in between them. There's not a decimal point anywhere. This is just 2 sig figs as well. Pause the video, see if you can figure out D through I on your own. All right, you can check your work against what I've got on the screen. Be careful with questions like letter D. This trailing 0 is not significant. There's no decimal point there to make it significant. However, it is significant in this measurement. All of those are significant. You've got sandwich rule, you've got zeros to the right of a significant figure where there are decimal points present. So all of those are significant. We did question G is very similar to question B. Those lead zeros are insignificant. So it's just the 3 sig figs. And when you're talking about numbers that are in scientific notation, you only pay attention to the coefficient. So both of those examples have 2 significant figures. As far as significant figures are concerned, numbers like this, 500 milliliters, often cause students some problems. It's possible to express 500 milliliters to a variety of different significant figures using scientific notation. The way it's written right now, technically there's only one significant figure, the 5. Some people kind of get cheap about it and try to put a decimal point in there, and now all of a sudden those other 2 zeros are significant, but that's not really the way that you should be doing things like that. So we know that zeros to the right of non-zero digits and numbers without decimal points do not have a definite number of sig figs, or they're not going to have as many sig figs as you'd like to express. So we're going to use scientific notation. If I want to express 500 milliliters to just one significant figure, I can do so by writing 5 times 10 to the second milliliters. That gives me just the 1 sig fig, as it's only the coefficient where we pay attention to significant figures. If I need 2 sig figs, I can call it 5.0 times 10 to the second. And finally, with 3 sig figs, it's 5.00 times 10 to the second. This is going to clear up any ambiguity with the measurement. So make sure you're using scientific notation when needed to express the correct number of significant figures. There are some numbers where we don't have to worry about sig figs, and they're called exact numbers. Numbers that come from definitions are exact. For example, there are 24 hours in a day. There are 100 centimeters in a meter. These are definitions and are correct to an infinite number of significant figures. Numbers derived from counting are exact. So I could go through, and if I was taking an average of 3 numbers, let's say, I don't have to pay attention that the number 3 is only contains one significant figure. I can just disregard it because that's considered an exact number because it was derived from counting. So I could say there are 10 sheep here. It doesn't really matter how many sig figs there are. We just consider it correct to an infinite number. If you take a measured value, whether it's a temperature, a mass, a volume, so on or so forth, they are never exact. That's where you always have to do some rounding, and you have to pay attention to sig figs. So again, it doesn't really matter if it's a digital instrument or if it is analog. If it's a measured value, it is not an exact number, and you have to pay attention to sig figs. So for example, in that instrument that we've got here, this thermometer, 37.0 degrees Celsius has 3 significant figures, with the 10th place being estimated. Significant figures are most important when we're talking about calculations. There are 2 general rules. One you follow for multiplication and division, and that rule is to round the answer to the same number of significant figures as the least certain measurements. So in other words, you can just count the number of sig figs in each of your measurements that you're going to be either multiplying or dividing, and the one that has the fewest, that's the one that's going to dictate or determine how many sig figs your answers can have. So for example, if I take the number 2.90 times 14.25, I see 3 sig figs and 4 sig figs. Therefore, my answer can only have 3 sig figs. So I know if you punch that into your calculator, you'll get more than 41.3, but you have to cut it off because you don't know any more than 3 significant figures in your least certain measurements. Put a star next to multiplication and division. This is the sig fig rule that you're going to be using most often. Addition and subtraction has a different but similar significant figure rule. In this case, we're going to round the answer to the same number of decimal places as the value with the fewest. So instead of looking at sig figs in total, we're looking for places after the decimal point. So if I take these two numbers, 7.050 plus 6.2, I've got 3 places after the decimal point here. I only have 1 in my second value. So when I add these numbers together, I really can only have 1 place after the decimal point. So I've got to round this to 13.2 so that these two are the same. You'll get better at this just with the more practice you do. The last thing I really want to talk about in this lesson is dimensional analysis. Dimensional analysis is a really powerful technique that you can use to convert between units. If you can get your units to work, in other words, cancel out the units you don't want and get the units you do want in the correct location, you're going to be able to solve all sorts of problems. So this is a really valuable skill that's going to serve you well, not just in chemistry courses, but in other classes as well. So basically, we've got what's called the desired unit. So we know what unit we're trying to get into. We've got the given unit, and that's going to be provided in the question. You've got what's called a conversion factor, and conversion factors are just fractions that are equivalent to 1. You might not know this off the top of your head, but 5 milliliters is equal to 1 tablespoon. Is that tablespoon or is that teaspoon? I think it's tablespoon. Regardless, so since these values are the same, whether I set it up with 5 milliliters in the numerator or 5 milliliters in the denominator, these fractions are equal to one another. I want to set up my fraction so that the desired unit ends up in the right spot. So I know if I need milliliters, not 1 over milliliters, I need to have milliliters in the numerator. And that my given unit, that is most likely not desired, is in a position where they can be canceled out. We know, hopefully from math class, that if a term shows up in the numerator and in the denominator, they're going to cancel. So that's exactly what we're trying to show here. And now you just get to do the math. 2 times 5 is 10, divided by 1 still gives you 10. So your final answer would be 10 milliliters. So you've got the right unit, which should be the desired unit. So it's all about setting up these conversion factors so that you cancel out the units you don't want and that you keep the units that you do want. Let's walk through one together. Let's say for whatever reason you want to try to convert 9.58 seconds into years. So really the first thing that I always do is rewrite the given number and units. And I'm not sure how much room I'm going to have to do this. I'll do it up here. So I've got 9.58 seconds. I'm going to abbreviate seconds with S. I've got to figure out the unit that is needed. And more often than not, you'll be told. In this case, I know I'm trying to get into years. Next, I want to use fractions equivalent to 1 and work step by step to cancel out the undesired units. So I don't really know how many seconds there are in a year, but I know a whole bunch of other time conversions that can hopefully get me all the way to years. For example, let me just write this a little bit more neatly. 9.58 seconds. I know, that there are 60 seconds in 1 minute. If I want seconds to cancel out, I should put 60 seconds in the denominator. If I put it in the numerator, I end up with the unit seconds squared over minutes, which I don't think really mean anything. So that doesn't help us out. But if we've got seconds in the numerator and the denominator, now they'll cancel. Now I'm a little bit closer to years. I've got minutes. Next step, I know that there are 60 minutes in an hour. Again, minutes will cancel out. I'm left with hours. I know there are 24 hours in a day. Hours cancels out and leaves me with days. And I guess depending upon how technically you want to be here, I think it's safe to say that we've got 365 days in a year. Now my days cancel out. From here, it's really just a math problem. I can take 9.58 divided by 60, divided by 60, divided by 24, divided by 365, and I'm going to come up with a little teeny tiny number. To be more specific, I come up with 3.0377 times 10 to the negative 7th years. This is not correct to the right number of significant figures. These 1, 2, 3, 4 conversion factors are all definitions. So I'm limited by my one measured value, which in this case is 9.58. There are 3 significant figures in 9.58, so I can only have 3 significant figures in my answer. So I'd say they're 3.04 times 10 to the negative 7th years, and that's going to be equal to 9.58 seconds. Finally, you want to check and make sure that your answer makes sense. 9.58 is 9.58 seconds is a really short amount of time, so hopefully it's a teeny number of years. I don't know necessarily that my answer is correct, but at least it makes sense. When I'm talking about 10 to the negative 7th, I'm talking about a very small number, so at least this makes sense. And if you are wondering where this number came from, it's from Usain Bolt. Not this most recent Olympics, but I think this is his world record holding time. We're going to do some more work with conversion factors, and you're probably going to need ones to get in between the metric and English system. So here are some that you should probably write down. You're going to need them for your homework. 1 inch is equal to exactly 2.54 centimeters. 1 pound is equal to approximately 454 grams. And 1 gallon is equal to approximately 3.79 liters. So this first number, since it is exact, has an infinite number of sig figs. These other two, you can take out to more sig figs if you'd like to. They contain a total of 3 sig figs. So let's go ahead and try out some practice problems with conversion factors. All right, I want to look at questions 2, 3, and maybe 4 if we've got time, just to practice with these concepts that we talked about. Question number 2 is telling us to convert 73 pounds into kilograms. The first thing you always want to do is just take the number and units you're given and rewrite them. Usually not a bad idea to put it over 1 just to help you keep your work organized. You want to convert this into kilograms. I don't know how many pounds are in a kilogram, but I do know the relationship between pounds and grams. I know if I have 1 pound, I have approximately 454 grams. Pounds has canceled out, and it's left me with grams. In order to get from grams to kilograms, I need another conversion factor. I know that there are 1,000 grams in a kilogram. I've got now the desired unit, in the correct place, kilograms in the numerator, so now I'm ready to just kind of set up and do my math. When you punch this into the calculator, you end up with 33.142 kilograms. We can't have that many significant figures. I see an infinite number of significant figures in my kilograms to grams conversion. I see 3 sig figs in my grams to pounds conversions, and my measured value has 2 significant figures. This is a multiplication and division problem, so I need to use the number of sig figs that are the same as the one with the fewest. So I can only have 2 significant figures, so I'm going to call this 33 kilograms. Let's do question number 3. Convert 962 gallons into milliliters. Okay, again, start by writing the number that you've been given along with the units. I don't know the relationship between gallons and milliliters, but I do know it between gallons and liters. I know if I've got 1 gallon, it's got a volume of 379 liters. That gets gallons to cancel out, and I'm left with liters. The question is asking me about milliliters. There are 1,000 milliliters in a liter. Now liters has canceled out, and I'm ready again to perform a calculation. Make sure that when you're performing calculations, you're keeping significant figures in mind. 3 sig figs, 3 sig figs again, and then 4 sig figs. Actually, wait, no, that's not true. I've got an infinite number of significant figures here because that's a conversion definition. So when I do the math, I can have 3 sig figs, so I get let's call it 65 times 10 to the 6th milliliters. Does that answer make sense? Well, a gallon is a whole lot bigger than a milliliter, so if I have almost 1,000 gallons, I better end up with tons and tons of milliliters. The exponent times 10 to the 6 is definitely telling me that I've got a big number here. The key to making sure that you're doing these correctly is to work step by step. Don't try to skip steps. Don't try to save yourself 2 seconds of writing. You really want to put it all down step by step. Students who organize their work this way tend to be a little bit better at this than students who either don't organize it, try to do it all in a calculator, forget to write their units or choose not to, or try to follow a different format. This is going to allow you to show your work, to cancel units out in a very organized way, and hopefully to get all of your thoughts down on paper. This way, instead of just giving me a number in a calculator, asking is this right, I can really see what you're doing. And this is going to prove to be really helpful as we build on this unit. My suggestion, as always, is to go through and try to tackle more of these practice problems. You need to get good at this. This is an important skill that we're going to use for the rest of the school year. So I hope you found this tutorial helpful. Thanks for tuning in, and we'll talk again soon.